Hello, this is Scholar Strife doing some math. Today we'll be working with sequences and series. Now, for a lot of you, this will be pretty difficult stuff because we're just looking at looking at a list of numbers, and we're trying to either make it into a formula or make it simpler, or let's just go through this here. So I'm going to skip this first example about the Tower of Hanoi. It's important. If you wanted to copy that down and then go check it out. Don't know if it's still there. But here we go. A sequence is a function whose domain is a set of consecutive integers, usually starting with 1. And then the domain gives the order. So we're just talking about a list of numbers here. Let's say 1, 3, 5, 7, 9, ... So this is my sequence. My domain is usually, here's my domain, usually 1, 2, 3, 4, 5, ... n, where n is the last number. So the domain, you just count them off. This is the first term, this is the second term, third term, fourth term, fifth term. And then your range is actually your sequence, the values that you have. So that's what this example means down here. So a finite sequence is a sequence that has a limited number of terms. Basically it ends, there's no ... So, for example, 1, 4, 9, 16, 25, it stops at 25, it doesn't go any further. So my domain for this one, like this is the first term, this is the second term, third term, fourth term, there's only 5 terms. So your domain would be 1 through 5. Number 4, infinite sequence that has an infinite number of terms, so hence the triple dot, goes on forever. Explicit rule, it gives an as a function of that term's position number in the sequence. And we call that position number n. So let's do an example of what that means. So this is the explicit rule. So if I wanted to know the first, for example, we want to know the first 6 terms. So this is the rule. So all I do is, if I want to find the first term, I just plug in 1 in the equation. So 1 minus 1 is 0, and negative 2 to the 0th power is 1. Put in 2 now. 2 minus 1 is 1, so I got negative 2. Put in 3. 3 minus 1 is 2. Negative 2 squared is positive 4. Put in 4, I'll get 8. Because 4 minus 3 is 1. Negative 2 to the negative 3rd power, or negative 2 to the positive 3rd power is negative 8. And then 5. 5 minus 1 is 4. Negative 2 to the 4th power is 16. And then 6 would be negative 32. Okay. So once again, here's my domain, and then here's my range. This is mostly what we're looking for here. Normally you can just leave off the domain. B, here's another one. It's not listed as a to the n, but this is basically the same thing. So the first term, plug 1 into the equation. I get 1 over 1 plus 1, which is 1/2. If I plug in 2, I'll get 2 over 2/3. 3, I'll get 3 over 4. plug in 4, I'll get 4 over 5, 5 over 6, and 6 over 7. Okay, part 2. Now we want to write a rule for these sequences. So we're going backwards here. They give us our numbers here. So we need to figure out what's going on with these patterns. So one way to do it is to look at what's going on with... So one thing you would look for is, you check the difference. So -1 to -8, that's adding -7. But 8 to -27 is -19. And then -64, that's going to be, well, basically what I'm saying is that these aren't matching up. There's no viable pattern, so that doesn't work. So looking for the differences doesn't work. So we try like multiplication. Let's see, -1 times 8, so I'm timesing by 8 here, and then 27, how do I get to 27 from 8? That's like 3 point something, so we know that multiplication doesn't work. But if we notice here, remember, our formula is going to look like this: a sub n equals something happens to our value. In this case, we take -n and take it to the cube power. So if you look at it closely, we have -1. So my first term is -1. So if I plug 1 into my equation here, I'll get -1 to the cube power, and that'll be -1. Plug 2 in, and I'll get -8. Plug 3 in, get -27. Plug 4 in, get -64. Part B. And it's all about seeing the pattern here. So always start off with try to look at your differences. So I have 5, 7, 9, and that looks like a steady pattern here. Looks like we start off with 3, and we add 5, and then we add 7, then 9, then this one would be 11, and then so on and so forth. So how do we write that as an equation? So we have a sub n and so remember, this is still 1, 2, 3, 4. So when I plug 1 into this equation, I have to get 3. But when I plug in 2, I have to get 8. And when I have to plug in 3, I'll have to get 15, and plug in 4, I'll get 24. So we know is once we know we have to add 2, right? So we start out with n and we add 2, and that's how we get 3 for our first one, right? But if I plug 2 in this equation, I get 4. So I need to multiply this by something, which in this case it's n, in order to make it work. So if I plug 1 in this equation, 1 times 3 is 3, 2 times 4 is 8, 3 times 5 is 9, and then so on. So one way to look at it is I needed n plus 2, because if I plug 1 in, I'll get 3. But I needed to find, I had to, but that doesn't work for if I plugged in 2, plugged in 3, plugged in 4. So you need to mess around with this until until you got the correct formula. Now, I know this is very confusing, but as you work with these, then you start seeing patterns. It starts to get a tiny bit easier. Let's look at a picture one. So diagram 1, we have 3 blocks here, and then it becomes 5, and then 7. So this is the first, this is the second, this is the third. So as you can see, we're just adding 2 each time. So once again, I can try n plus 2 again, and that doesn't work because 1 plus 2 is 3, and then 2 plus 2 is 4, so that doesn't work. So we have to kind of examine what's going on in this picture. I'm starting off with a corner block, and then I tack on 1 here and 1 here. So 1 plus 2, 1 plus 4, and 1 plus 3. Or 6. Yeah. So notice how this 1 is constant here. So in my formula, we're going to have something plus 1. Now that we know that that's true, think of it this way. What number do I have to multiply to get sorry. Working with a cold. So what I'm trying to say is, so the 1 is constant, so we're adding 1 to something, and what's going on is we're adding 2 more each time. So every time we go from one diagram to the next, we're adding 2. So that's where that 2n comes from. So we're adding 2 each time, and then we're starting off as 1. Okay. So here is my formula. So I'm adding 2 here and 2 here, adding 3 here and 3 here. So I'm adding, yeah, okay. Hopefully that makes a little bit of sense. Series 6, the sum. And remember, sum means addition of terms in a sequence. So for example, 1 plus 2 plus 3 plus 4 plus 5 plus 6, or that would be an infinite series there. Number 7, moving on. We represent these series usually using this sigma notation, this weird. So this symbol here is called sigma. And the index of summation is I. That's basically our domain. So we're plugging in values of 1, 2, 3, 4, stuff like that. And then the lower limit is usually 1, and then we have an upper limit of summation. And this is n. So the index of summation is usually your domain. It starts off as 1, and then we plug in 2, the first term, the second term, the third term, the fourth term. So we plug 1 in the equation, 2 in the equation, 3 in the equation, 4 in the equation. This I right here is the equation itself. So for example, if this I was 2x, I would plug 1 in the equation and get 2. Plug 2 in the equation, I would get 4. N is the number you stop at. So n is the number you stop at. So here we go. The finite series, limited number of terms. Infinite has infinite number of terms. So for example, so here's I squared, that's the equation. If I plug 1, I'll get 1 squared, and that's the first term. If I plug in 2, I'll get 4. If I plug in 3, I'll get 9. If I plug in 4, I'll get 16. And if I plug in 5, I'll get 25. And then you would just add them all up, because this is a summation. So the sigma term, once again, is called summation. So infinite series, so we start off with 1, this is the first term, and then we got 2, 3, 4, and then dot, dot, dot means infinity. Okay, part A. So we want to use sigma notation. So we start off by doing that. Usually I equals 1, because this is 1, 2, 3. Okay. And we notice that we're adding 5 more each time. So this will be the 20th term, because 100 divided by 5. So I'm going to put 20, because that's my last term. That's how many we're going. And then my equation is 5i. 5 times 2 is 10, 5 times 3 is 15. So what this sigma notation says is, sigma means sum. I want the sum of all the terms from the first term all the way to the 20th term of this equation here, 5i. So what it means is 5i, so I plug 1 in, get 5. Plug 2 in, get 10. Keep this going on, process until the 20th, and then add all those numbers together. But right now we're just writing notation. We're not actually adding anything up yet. Okay? So here's the first term, here's the second term, here's the third term, here's the fourth term, here's the dot, dot, dot. And there's no ending term, so draw sigma. I equals 1, and we're going to infinity, and now we got to figure out our equation. So when you're dealing with fractions, you kind of want to see them separately as 2 different patterns. So for example, if I look just at the top, 1, 4, 9, 16, we'll notice that the top is actually I squared, right? I plug in 1, I'll get 1 squared, 2 squared is 4, 3 squared is 9, 4 squared is 16. And then the denominator, if we look at it, so 2 to 5 is plus 3, 5 to 10 is plus 5, apply 10 to 7 is plus 7. So how do we represent that? That'll be I squared plus 1. And so so the difference is plus 3, plus 5, plus 7. How do we write that? It's I squared plus 1, but another way to look at it is, notice from the top to the bottom, the numerator and denominator, I'm just adding 1, right? From 4 to 5, I'm adding 1, 9 to 10, I'm adding 1, 16 to 17, I'm adding 1. So I have I squared up top, and then on the bottom, I still have I squared, I'm just adding 1. So like I said, it's very difficult to find these patterns, but for this first section, we're kind of looking at them, and make sure you look in the back of the book at your answers, kind of practice these. In the next couple sections, we're going to actually have some rules that we can use to help us figure out some of these patterns a little bit easier. But for now, we're just looking at kind of general patterns. So, right here, part C, you got 6, 36, 216, 1296. These look like powers of 6 to me. So if I plug in 1, I'll get 6. If I plug in 2, I'll get 36, 3, 4. So we have sigma notation going on to infinity, starting at 1. This is 6 to the, so instead of n, we use the letter I for sigma notation. Why? I don't know. It's just the letter they want to use for a different thing. Well, they use I as index, I guess. That's why. But this one is a little bit easier to see. You know, I plug in 1, I'll get 6. Plug in 2, I'll get 6 squared. Plug in 3, I'll get... and so on and so forth. Part D. So it looks like we're adding 1, adding 1, adding 1, adding... Yep. So 5 plus 6 plus 7 plus 8 plus 9 plus 7 plus 11 plus 12. So I equals 1. So 1, 2, 3, and then 4, 5, 6, 7, and then this would be the 8th term. And sorry, I forgot the placement, the actual placement, so sorry if you've been watching closely. You're supposed to place the top number, or your n value, on top. Okay. And this was 5i. And your bottom number on the bottom. So your starting number is on the bottom, and it's usually I equals 1, and then your ending number is on top. And then your equation is supposed to be right there next to there. Alright, back to D. If I plug in 1 in, I'll get 5. And then, so this is I plus 4. Plug in 2, I get 6. Plug in 3, I get 7, and so on and so forth. That one hopefully is a lot easier to see. Alright. Number 5, find the sum of the series. Now, j equals 3. So it's saying start with the third term. Okay? So the third term is plug in 3 into the equation. There's G. So 5 minus 2 times 3. That is 5 minus 6, which is negative 1. Okay? And now what it says is start at 3 and end at 6. So I'm going to plug in 4. Plug in 5. And plug in 6. And then we're going to add all of these together. Okay. So if I plug 4 into this equation, I'll get 5 minus 2 times 4. Plug in 5. 5 minus 2 times 5. 5 minus 2 times 6. So 5 minus 8. 5 minus 10. 5 minus 12. So 5 minus 8 is negative 3. 5 minus 10 is negative 2. And 5 minus 12 is negative 7. Oops. Sorry. 5 minus 10 is not negative 2. Negative 5. There we go. And then we just add all our answers together. So negative 4 plus negative 12. So negative 16. And that's our answer. Okay. So this is my starting number. J equals 3. And we're going to, we start at 3. Normally we start at 1, but this time they wanted us to start at 3. Let's look at another example. Or not. So memorize these special series here. So this is the sum of n terms. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 ... This is the sum of the first n positive integers. Oh, sorry. Let me start over there. So the first one was actually the sum of n terms, which means 1 plus 1 plus 1 plus 1 plus 1 plus ... This one is the sum of n positive terms, so 1 plus 2 plus 3 plus 4 plus 5 plus ... This one here is the sum of squares. Sum of squares of the first positive n integers. And if all that is Greek to you, what it looks like is 1 squared plus 2 squared plus 3 squared plus 4 squared ... all the way to n squared plus. Alright, part 6. Use a formula to find the sum of I equals 1, from the sum from I equals 1 to the 25. Okay. So, this is the second equation. Right here. So what it's telling us is that it's equal to this formula here. So n plus 1 over 2. That means we just plug 25 in. So 25 plus 1 divided by 2, which is 650 divided by 2, which is 325. So if I add 1 plus 2 plus 3 plus 4 plus 5 dot 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 plus 6 or plus, well, dot 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 plus 24 plus 25, that'll give me 325. So that's what these three special formulas give you, is if your equation looks like this, then if you just want to add 1 plus 1 plus 1 plus 1, you just add the last, that'll equal be the last number, whatever you're putting in. If your sum looks like this, 1 plus 2 plus 3 plus 4 plus 5 plus dot dot dot, you just plug in your last term into this formula, and that'll give you the total sum. And lastly, if you have 1 squared plus 2 squared plus 3 squared plus 4 squared, you can plug that, the last number, into this equation, this third equation here, in order to get the total sum. Hopefully this wasn't too confusing for you. Make sure you look at your patterns closely. Make sure you look at the answers. Practice a little bit. It's a bit confusing, but if some of you will have the knack for finding these patterns. All right. Have a good day.